Good day, students. Welcome to part 2 of the definite integral review. Let's go ahead and take a look at question number 1. For number 1, we are to evaluate the following expression. Evaluate the definite integral from 0 to 3 of the derivative d dx of xe to the 3x dx. Okay? Alright, so let's go ahead and evaluate this. So if we think about it, if you're evaluating a definite integral, what do you do first? First thing you do is you take the antiderivative of the integrand, and then you evaluate it at the limits of integration. Okay, so another way I can write this expression right here is basically find the definite integral, find the indefinite integral of this expression, the derivative d dx of x e to the 3x dx. Okay, now after finding the indefinite integral, whatever the result is, I'll evaluate it from 0 all the way to 3, right? So evaluate it from 0 to 3. But if you look at this situation right here, what is the relationship between the integral and the derivative? They are inverse operations. Okay, so when you're looking for the indefinite integral of the integrand, which starts with a derivative, these two operations basically neutralize each other. They cancel each other out. So what you're going to be doing in actuality is evaluating this expression right here, x e to the 3x from 0 to 3 using FTC part 2. Okay, so what does this mean we should do? We evaluate this expression at the upper limit minus this expression evaluated at the lower limit. So we're going to have 3e to the 3x, I'm sorry, e to the 3 times 3. Plug in 3 into the 2 x's. 3 times 3 minus 0 times e to the 3 times 0. You can clearly see that this entire expression is 0, and you're left with 3 e to the 9th power. Alright, so there goes your final result. Alright, let's take a look at question number 2. It says, given the graph of the acceleration of a particle below, so this function right here, f of x, is the acceleration of a particle, and the velocity is given by v of t equals the integral from 1 to t of f of x dx. Find the following. Alright, so let's start with the a part. So with the a part, we have to find two things, v of negative 2 and v of 3. So let's start with v of negative 2. So v of negative 2 just involves substituting negative 2 for t here. So how does that affect this expression? It makes it the integral from 1, instead of all the way to t, is going to go to negative 2 of f of x dx. Alright? So we know what the integral, the definite integral is, right? Is the area underneath the curve, between the curve and the x-axis. So if we look at this order of integration, you'll notice that it's actually going in reverse order. You're going from 1 to negative 2. So can we switch the order of integration here? The answer is absolutely, we can. So let's go ahead and do that. We can write this as negative of the integral from negative 2 to 1 of f of x dx. So we're looking at the area underneath the curve from negative 2 all the way to positive 1. Alright? Alright, so let's go ahead and evaluate this. So if we do that, we're going to have a composite shape. We have a triangle here, and we have a square. Okay? So if we do the area of this triangle from negative 2 to 0, that's going to be 1/2 of the base the base is um, 2 units long, half of the base times the height. Since it's going upside down, we're going to have a negative 1 unit as a height. Okay, and then plus the area of the square, the width is 1, and the height, since it's going down, is negative 1. So we don't want to forget this minus that we factored out, so let's put the minus in front here. Alright, so remember this is the area of the triangle, this triangle right here, plus the area of the square, this square right here. So that's going to yield negative, this entire expression, these two 2's cancel out, negative 1, 1 times negative 1 is negative 1, minus 1. Alright, so you have negative times negative 2, and your final answer is 2. Alright, so for the second part of part A, we have to find v of 3. So let's just call that double I. V of 3 is similar to this. We're going to look for the integral from 1 to 3 of f of x dx. Okay, so in this case now we're going from 1, we want to look for this area, all the way to here, this area right here. Okay, so what can you guess what the answer is just by inspection? These two areas are identical in size, but this is negative and this is positive. So what happens when you add two identical opposite quantities? They cancel each other out to 0. So this should be 0. Okay? Alright, let me show you the mechanics to prove that that is actually the case. So let's use geometry here. So the area underneath this curve is 1/2 base times height. Let's go ahead and compute that. We're going to have 1/2 times the base, which is 1 unit long, times the height. Now, since the height is going downstairs, underneath the x-axis, or it's upside down, is going to be negative. All right, plus the area of this triangle on this from 2 to 3 is 1/2 base of 1, height of positive 1. Okay, and you can clearly see we have negative 1/2 plus 1/2, which equals to 0. All right, let's move on to part B. Part B, we have to find the maximum velocity for this particle and where it occurs. Now, f of x is equal to the acceleration, and we know we have the continuum, position, velocity, acceleration, and jerk. So the acceleration is the derivative of the velocity. So this graph right here is equal to v prime of x. Okay, so this is v prime of x. To find the max, we want to look for where the function changes from increasing to decreasing. Okay, that's where you have your maximum located at. Remember, the sign of f prime tells you the direction of f. Okay, so let's do a number line. If you want to find what we're looking for here is the extrema. That's what we're looking for. So using this graph of the derivative of velocity, let's see, we're going to connect the sign of v prime, which is a, with the behavior of f. Okay, so we see a sign change here, negative 2. We see a sign change here, positive 2. Okay, so remember what we're looking at is a sign of v prime. Okay, and that tells us the behavior of v. Okay, and v prime is also the same thing as a. So from negative 3 to negative 2, so v prime is negative, which means, I'm sorry, it's positive because it's above. This is positive and this is negative. So this is positive, so that means that v, the velocity, is increasing. From negative 2 all the way to 2, it's underneath the x-axis, which means that the v prime is negative, indicates the function is decreasing. And then from 2 all the way to 5, v prime is positive, which indicates that the function is increasing again. So if you go from increasing to decreasing, what is this extrema? What can you classify this extrema as? If you're increasing and you start to decrease, this right here is a maximum, a relative maximum on the domain. And on this extrema right here, if you're decreasing and then you start to increase, this is a what? This is a minimum. Okay? So this clearly shows us, since you're going from positive to negative, that you have a maximum. That's the only maximum we have at t equals negative 2. Alright, let's take a look at question letter C. It says, when is the jerk of the function less than or equal to 0? Okay, when is the jerk of the function less than or equal to 0? So, how do you get jerk from acceleration? You know that a prime is equal to jerk, derivative of acceleration. So if this is the acceleration curve, what is the derivative of the acceleration? That's the question. The derivative of the acceleration graphically is the slope of the tangent line at every point. So since these are all straight lines, the slope of the line can basically tell us what the slope of the tangent line is, since they're basically the same line. Okay? Alright, so we're looking for where the jerk is less than or equal to 0. So basically we're looking for where the slope of the line, slopes of A is either equal to 0 or negative. Okay? So let's look at this line. Where do we have negative slopes? So from here you can see that the acceleration is decreasing from negative 3 all the way to negative 2. So guess what? A prime is negative on this interval right here. The slope is always negative. Here, the slope is going to be what? Here the slope, A prime is equal to 0, since you have a horizontal line. Okay? And then here it's positive, we don't care about that. And then from 3 to 4, A prime is equal to 0 again. And then from 4 to 5, A prime is negative. Alright, so when we're looking for where it's negative or equal to 0, our answer is going to be as follows. It's going to be in the intervals from negative 3 to negative 2 and then to 0, because only negative 3 to negative 2 to negative to 0 for negative, and then all the way to 1 for 0. They both included. So from negative 3 to 1, and then from 3 to 5, because it's 0 and then negative from 3 to 5. So this is where your jerk is less than or equal to 0. Okay, so don't forget that A prime of t, the derivative of acceleration, is your jerk. Okay? Alright, let's take a look at option letter D. We're to find the intervals where the velocity is decreasing. So V of t is decreasing when V prime, which is equal to A of t, is what? Negative. Okay? So we have to go back to the graph and look for where the acceleration is negative. Anywhere the acceleration is negative, that means that its derivative, which is velocity, is going to be decreasing. Okay? So you notice we already talked about it here. From negative 2 all the way to 2 is decreasing because the acceleration is underneath the x-axis. Remember, this is your acceleration curve. Okay? So V is decreasing from negative 2 all the way to 2 because its derivative, because V prime of t is negative on that domain. So that's that. All right, let's take a look at question number 11. I'm sorry, question number, where are we at? Question number 3. So for question 3, we're going to be using um, the rules of integration. So we have to find um, k, so that um, the integral from 2 to t of 2 root x dx plus k is equal to the integral from 5 to t times 2 root x dx. Okay, so in order to do this, we have to look for a way to isolate k and combine these two integrals into one if possible. Notice they have a similar limit of integration. So if they have a similar limit of integration, then it's possible for us to combine them. All right. So what I'm going to do is I'm going to move um, this integral to the left. So we have k equals the integral from 5 to t times 2 root x dx. So you got to subtract this integral from both sides. So it becomes minus the integral from 2 to t times 2 root x dx. Now in order for us to stitch these two integrals together, we have to make sure that the upper limit of one corresponds to the lower limit of the other. All right, we can clearly see that that's not the case here. So on this integral, we can switch this around using the order of integration rule. So this becomes the integral from 5 to t of 2 root x dx. Try that properly. 2 root x dx. Fix that. And then we're going to switch the order of the other one. 2 root x dx plus the integral from t to 2 of 2 root x dx. Alright, so this now becomes the integral. We can now combine them together from 5 all the way to 2 of 2 root x dx. That's what k is equal to. And then if we want to put it in ascending order, we can use the order rule of integration again to write this as the integral, the negative of the integral from 2 to 5 of 2 root x dx. Okay, so you remember that if you switch the order, then you have to introduce a negative. So let's go ahead and evaluate this integral using the integration rules. So we're going to have, let's express this as factor out negative 2 from 2 to 5 of x to the 1/2 dx. Now what's the antiderivative of x to the 1/2? It's simply going to be x to the 1/2 plus 1 over 1/2 plus 1. Okay, so this is going to be negative 2x to the 3/2 over 3/2. And then if you simplify this, you have negative 4 over 3. That's if you reciprocate 3 over 2 and multiply by the top, you get that. X to the 3 over 2. Okay? So remember, we're evaluating this from 2 to 5 to get up the value of k. So k is going to be equal to, you're going to plug in the upper limit, negative 4 times 5 to the 3 over 2 over 3. And then you plug in the lower limit minus, well, let me make our lives easier here. So to avoid too many complications, I can factor out this negative 4/3. Okay, let's go ahead and do that. So put the negative 4/3 out here. I don't want to keep writing it over and over again. And then we're going to evaluate x to the 3 over 2 from 5 all the way to 2. Okay, so this is going to become negative 4 thirds times 5 raised to the 3 halves power minus 2 raised to the 3 halves power, like that. So we can write this as negative 4 thirds times, we can break this apart. This is 5 times 5 to the 1 half, right? 5 to the 1 times 5 to the 1 half minus 2 to the 1 times 2 to the 1 half. Remember, when you multiply exponents, you add the powers, right? So when you split them, you can subtract the powers, express them separately like this, okay? So finally, we can write this as negative 4 thirds times 5 root 5 minus 2 root 2, okay? So there goes your final result. All right, let's take a look at the last question, question number 12. I'm sorry, question number 4. So for problem 4, we're to find F4 if the integral from 1 to x of f of t dt is equal to x to the sine x. Okay, so we're going to go ahead and look for this. So to find this, to find f of 4, first thing we have to do is find f prime of 4, okay? I mean f prime of x, and then evaluate it at 4. So f prime of x is equal to, is basically the derivative of the integral from 1 to x of f of t dt, which is equal to the derivative of this expression x to the sine x. Okay? Now, if you have a situation like this, a function raised to a functional power, we're going to have to use um, logarithmic differentiation. Okay, so let's say y is equal to this function right here, x to the sine x. Okay, we want to use a variable that we can solve explicitly for. So now if we differentiate both sides, that will be basically be what dx of this expression is. But before we do that, we need to power down this exponential function. So what we'll do is we'll take the natural logarithm of both sides. So ln y is equal to the natural logarithm of x to the sine x. Now using the properties of logarithms, I can power this exponent down. So this can be written as the natural logarithm of y equals sine x times the natural logarithm of x. Okay? Now we're going to differentiate this side, both sides of the equation. Alright? So if we want to differentiate both sides, let's rewrite it again. So ln y prime equals sine x ln x prime. So on the left side, using implicit differentiation, we're going to have the derivative of ln y is 1 over y times y prime. And on the left side, we're going to use the product rule. So this is u, and this is v. So we're going to have vu prime ln x, derivative of sine x is cosine x, plus, so this is vu prime plus u v prime. So u is sine x, and the derivative of ln x is 1 over x, so sine x over x, like that. Okay, so if we want to get y by itself, y prime by itself, y prime is equal to y times ln x cosine x plus sine x over x. But we know what y is, right? Earlier we said that y is equal to x to the sine x. So that implies that y prime is equal to x to the sine x times ln x cosine x plus sine x over x. Okay, so this is what uh, this is what f of 4 is. Okay, so this is what f of 4 is. So what we're going to look for now is this is f of x. Okay, this is f of x right here. So let's, I made an error in my notation. This is supposed to be find f of x. Okay, f of x, since this is the integral of f of x, so f of x would be the derivative of this entire expression. So this is right, this is f of x, sorry about that. Alright, so if this is f of x, what is f of 4 going to be? F of 4 is simply going to be what you get when you evaluate this function at x equals 4. So you're going to have 4 raised to the sine of 4 times the natural logarithm of 4 cosine 4 plus sine 4 over 4. Alright, so there goes your final result. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel. And please post a comment to let me know what you think about this clip. More clips can be found on math.serve.com. Thanks again for watching, and have a wonderful day.